Welcome back. In the last video we have discussed so far the indirect maximum power point tracking techniques. In this video I will continue the discussion on the maximum power tracking technologies. Now let's look at the more involved kind of maximum power point tracking, the direct maximum power point tracking. This kind of maximum power point tracking involves direct measurement of current, voltage or power and a more accurate, faster response than the indirect method. Due to time constraints, we shall look at a couple of the most popular kind of algorithms, which are sometimes also classified as hill climbing algorithms. We start first with the perturb and observe or PNO algorithm. In this algorithm, a perturbation is provided to the PV module or array voltage. This would translate to an increase or a decrease in power. If an increase in voltage leads to an increase in power, this means that the operating point is to the left of the maximum power point, and hence further voltage perturbation is required towards the right to reach the maximum power point. Conversely, if the increase in voltage leads to a decrease in power, this means that the current operating point is to the right of the maximum power point, and hence further voltage perturbation is required towards the left to reach the maximum power point. In this way, the algorithm converges towards the maximum power point over several perturbations. You would have noticed that this algorithm takes advantage of the fact that the PV curve has an increasing nature to the left of the maximum power point and a decreasing nature to the right of the maximum power point. The problem with this algorithm is that the operating point is never steady at the maximum power point. It is always hovering around in the maximum power point region, although this could be minimized using very small perturbation steps around the maximum power point. This algorithm also struggles under rapidly changing illuminations. For example, if the illumination and therefore irradiance changes in between two sampling instants in the process of convergence, then the algorithm essentially fails in its convergence efforts. This situation is illustrated in the figure as well. In the latest perturbation, the algorithm has determined that the maximum power point lies to the right of point A, and hence the next step is a perturbation to converge towards the maximum power point accordingly. However, as the illumination changes rapidly before the next perturbation shifts the operating point to B, while the new maximum power point actually moves to the left of B. This can be severely erroneous because the algorithm has now reached at point B such that the power at point B is larger than the power at point A. But the maximum power point still lies to the left of point B, which makes the algorithm think that the maximum power point is to the right of point B. This is detrimental to the speed of convergence of the PNO algorithm, which is one of the critical figures of merit in the field of the maximum power point tracking techniques. Thus, drastic changes in weather conditions severely affect the algorithm's efficiency. Next, we look at another kind of direct maximum power point tracking algorithm called the incremental conductance method. To better understand the algorithm, we shall first arrive at a relation between the conductance and incremental conductance. Conductance of an electric component is nothing but a ratio of the current to voltage, or in other words, reciprocal of resistance. We know that at the maximum power point, the slope of the PV curve is 0, so dP dV is equal to 0. Now, dP dV could be written as d current multiplied by voltage dV. Using basic differentiation, we get dP dV is equal to the current plus voltage times di dV. If the sampling steps are small enough, then di dV could be approximated to delta I delta V. Thus, at maximum power point, delta I delta V is equal to minus I divided by V. To the left of the maximum power point of the PV curve, delta I divided by delta V is larger than minus I divided by V. And to the right of the maximum power point on the PV curve, delta I divided by delta V is smaller than minus I divided by V. The algorithm exploits these basic facts about the IV and PV curve of a solar module. In general, the algorithm imposes a voltage on the PV module at every iteration, measures the incremental change in conductance, compares it with the instantaneous conductance, and decides if the operating point is to the left or to the right of the maximum power point. I will explain this in a brief conceptual flowchart for a maximum power point tracking algorithm based on incremental conductance methods. The instantaneous voltage and current are the observable parameters, while the instantaneous voltage is also the controllable parameter. Vref is the voltage value forced on the PV module by the maximum power point tracking device. It's the latest approximation of the VMPP. For any change in the operating point, the algorithm compares the instantaneous and incremental conductance values. If incremental conductance is more than the negative of the instantaneous conductance, this means the current operating point is to the left of the maximum power point. Consequently, Vref is incremented. Conversely, if the incremental conductance is lower than the negative of instantaneous conductance, the current operating point is to the left of the maximum power point and the Vref is decremented. This process iterates until the incremental conductance is the same as the negative of instantaneous conductance, in which the chosen Vref is equal to the VMPP. This maximum power point tracking algorithm can be more efficient at the maximum power point, as it doesn't hover in the maximum power point region under steady state like the PNO algorithm does. Also, low sampling intervals make it less susceptible to changing illumination conditions. However, under very highly varying conditions and partial shading, the incremental conductance method might also be rendered less efficient. The main drawbacks of this algorithm is the complexity of its hardware implementation. It needs to not only measure the currents and voltages, but also calculate instantaneous and incremental conductance values. In modern PV systems, the function of the maximum power point tracking is often implemented within other system components like the solar inverters and charge controllers like shown here. Please note that the list of techniques and typical implementation are definitely not exhaustive. In fact, several algorithms and implementation techniques exist in practice as well as in literature. There are scores of scientific papers, patents, and proprietary technologies existing in this rapidly growing space. In view of time, we have covered only the most common or simple maximum power tracking techniques. In summary, maximum power is delivered from the PV cell module or array if the operating point is the same as the knee of the IV curve. An ideal maximum power point tracking device is not only able to track that knee under varying conditions, but also maintain the voltage and current accordingly. In doing so, the device is expected to use as low an energy amount as possible so as to not undo the additional energy gains the maximum power point tracking processes provides. The maximum power point tracking device is also expected to respond swiftly and accurately to changes in the ambient condition that impact the PV output. So, see you back in the next video.